motion first, then we will come back to questions and doubts in everything put together, projectile motion as well as straight line motion from the assignment I've given you before, etc. Anyhow, so let's begin. So in the previous session, we have seen the standard case of projectile motion. By standard case, we mean that when we project an object from a horizontal surface obliquely, and the particle comes back to strike the same horizontal surface or impact the same horizontal surface, then on the basis of these equations of motion, we saw that at any time t, if the velocity is v and the coordinates are x and y, taking this projection point as our origin, so our y-axis like this and our x-axis like this, then first of all we have the equations of motion, which are given by horizontal velocity is constant, vertical component of velocity is having a uniform acceleration of -g. So horizontal displacement component becomes u cos theta t, vertical displacement component becomes u sin theta t minus half gt square. So this set of equations is the most important thing. We can express them in vector form also. And then on the basis of this, we saw the calculation of the horizontal range is given by the formula u square sine 2 theta divided by g, or we can also write it as ux into time of flight. The total time of flight is 2u sine theta divided by g, or 2 times uy by g, and the maximum height is u square sine square theta divided by 2g, or uy square divided by 2g. So these were the standard quantities. This being the maximum height, this being the horizontal range, the particle reaching here at t equal to capital T. So this was one of the things, and we had also discussed about the symmetry of the projectile motion, as in the ascent and descent are symmetrical to each other in terms of time, in terms of position and velocity also. And then finally, we had also discussed about equation of trajectory. So this is just a brief recap of some of these things. We will discuss some related questions and things also today. And of course, we'll discuss the doubts.
Sir,
Yes.
the doubts from the assignment or like module?
Both. We try to clear all the doubts in kinematics so far today.
The last class you did not send any assignment.
Yes, sir.
Yes, I had asked you to do projectile motion questions from H.C. Verma. Okay.
You didn't pull the green off.
Sorry, I did not.
Yes.
Yes, sir, you did not told. I guess, sir, it might have been for the red house. After the batch shuffling, there might be little bit changes. So greenhouse.
Okay, okay. Anyway, so I will send you the questions again from projectile motion from H.C. Verma plus a separate assignment also, a revision assignment. Okay. Okay, so don't think we have discussed equation of trajectory. We had only discussed up to these formulae last time. So moving forward, just quickly let's discuss about the symmetry of the projectile motion. The symmetry is like that from t equal to 0 to t by 2, the particle, the projectile ascends. So the y coordinate goes from 0 to h, and similarly from the half time to the total time of flight, the projectile descends. As the y coordinate comes back from h to 0 to the ground level. So these two parts of the motion, if you divide the overall projectile into two sections of its motion, one while the projectile is ascending in height and the other when it is descending in height, you will see that the two parts are like mirror image symmetry with respect to each other. So this becomes a key in solving certain types of questions. You see that we projected it at u at an angle theta at t equal to 0. And as usual, it's ascending and then descending. So this aspect of symmetry that I was telling you about, this is noticeable in a number of things. For example, when it impacts the same ground level, the impact velocity will have the same magnitude as the projection velocity, and this angle will become theta. Similarly, when it reaches the highest point, not only the y coordinate has become h, but at this point, the velocity would have become horizontal. So it just would be u cos theta I cap. Okay, the time would be exactly half of the total time, and the x coordinate would also be half the range. So it's dividing this exactly into two equal halves. And not only that, now if I see some other position over here where the y coordinate has become some d, okay, where d is obviously less than the maximum height. So at this point of time, let's say the velocity is v1 and the time is t1 and the x coordinate is x1. Okay. I'll see that on its way down in descent also, it will go through some position where its y coordinate again becomes d. It's at the same level from the ground. So when it is at that position, if you look at the time, if you look at the velocity, and if you look at the x coordinate, you will notice that there's symmetry. So that symmetry is like this, that this distance from here to here, x1, should be equal to this distance from x2 to r. So we have that x1 is equal to r minus x2, or in other words, the sum of these two x coordinates is equal to r. This is happening if at t equal to t1 and t equal to t2, the y coordinate is common. Okay, then it implies that this will happen. Also, that the time taken to go from the projection point to this point will be the same as the time taken to descend from this second point here at t2 till where it hits the ground at capital T. So time also has that symmetry, that t1 will be equal to capital T minus t2. So that sum of these two times will be the total time of flight. And the other symmetry that is there will be that if v1 is u cos theta plus, u cos theta I cap, unit vector notation. So x component of course is uniform always, okay, but plus some vy j cap. Then it implies that your v2 at that other point must be u cos theta I cap minus of that same y component. So in other words, whatever the magnitude of v1, same will be the magnitude of v2. So these are the three aspects of symmetry, that x1 plus x2 is r, t1 plus t2 is capital T, and the magnitude of the velocity is the same in both these points of time, provided they satisfy this condition that the y coordinate is common at both of them. Okay. So we had seen this symmetry in a particular numerical problem with the analysis last time. So now you can just note it down as a point that it is to do with the symmetry of the projectile motion for the ascent part and the descent part. So I'll show you questions in which this symmetry is very useful to do a numerical problem solving.
So can you again like explain it from it at t is equals to t1 and t is equals to t2, y is equals to d?
Yeah, that is a condition that over here. You can see that we have selected 2 points when it is at the same height from the ground, but one is on the way up and the other is on the way down.
Yes, sir.
Adina, the x component of velocity is always uniform beta. That is throughout the projectile motion that you have seen in the previous section here. If you look at these equations, you can see that the velocity's x component is always uniform. So this is at any time t. Throughout the projectile motion, the velocity's x component remains constant. It's not just at t1 and t2. But it is the y components which become symmetrical for v1 and v2. If you compare those two vectors, now v1, if it is a vector like this, then v2 will be a vector exactly like this. It will be symmetrical. They'll both have the common x component of u cos theta, and they will have equal and opposite y components. This and this will be equal and opposite. This will be plus some vy. This will be minus of some vy. Okay, so let's understand a question based on this.
So can you just scroll it again for me?
Yeah.
Thank you.
R is the range, beta. Atharv. R is the horizontal range of the projectile. It is the distance at which it lands. Okay, so R is basically this whole distance here. This from here to here, this is the range. It's given by that formula that we discussed. R is the displacement from the initial point of projection till the impact point or till the landing point where it lands back on the ground. Okay. So these things we have already discussed carefully in the last lecture. Okay. Range, maximum height, total time of flight, the equations of the motion. Now we are discussing about the symmetry part, and we'll see how This can be used in a question. So, for example, a particle is projected from the ground at time t equal to 0, such that its height from the ground equals to, let us say, 40 meters at t equal to 2 seconds, and again t equal to some t2, which you don't know. If g is equal to 10 meters per second square and its range r is equal to 180 meters, then find its initial velocity of projection and angle of projection, maximum height, this time t2, and total time of flight capital T, and also the velocity at maximum height position.
Sir, can you show that graph once again?
Yeah, actually that's not a graph, Peter. That is the actual path of the projectile. You understanding? No? There's a difference between the two.
Yes, sir. There were arrows.
This is actually the actual path of the projectile in the xy plane, where y is the vertical axis, x is the horizontal axis. Graph, remember, is a representation of a function. So for example, if we were to plot x as a function of time or y as a function of time or something like that, that would be a graph. But in this case, this is the actual path of the particle. What in technical language of kinematics, we call it the trajectory. Trajectory is the path. This
Yes,
is the
sir.
actual path diagram. Okay, so this is clear now. Shall I come back to the question?
Yes, sir.
Okay.
So,
Yes.
so in this C sub part, you wrote that T2 and capital T, right? We need to find.
Yeah, capital T is the total time of flight.
Okay.
Okay, so see, the information that is given to us is this. Okay, it's given to us that the y coordinate of the projectile, that is the height from the ground, no? That is 40 meters at t equal to t 2 seconds, and again at some time t2, where t2 is greater than 2. Okay. So from this, how we can calculate? We can calculate, and the other thing that is given to us is the range. So given is this thing, and the range is 180 meters. Two things are given to us. Okay. Now see the first information that is given to us, that will help us calculate the vertical component. Okay. From this we know that y is u sine theta t minus half gt square. So in this, if I substitute the value of time as 2 seconds and the value of y as 40, I'll get u sine theta. And this will tell me what, that the range is u square sine 2 theta divided by g. Okay. So when we compare these two equations, there are two equations with two unknowns, u and theta. So we'll be able to solve both of them. Okay. So the first equation, if I substitute this information in the first equation, I'll get one relation between u and theta. Okay. And again, if I substitute this information in the second equation here, I'll also get another relation in u and theta. And then solving those two relations, I should be able to find the value of both u and theta. Okay. So let's do that. So on substituting this, what we'll get over here, we'll get that 40 is equal to 2u sine theta minus g will take as 10. So 5 into 2 squares, so 20. You see, we are getting the relation that 2u sine theta is equal to 60. This is what we are getting from the first equation. Or u sine theta is equal to 30. Okay. So directly we are getting one component of velocity, na? U sine theta. And now see, we'll substitute that in this equation. So we'll get 180 is equal to u square sine 2 theta divided by 10. So basically u square sine 2 theta is 1800. Okay, this is what the second equation is telling us. And we have u sine theta is equal to 30. So if I just divide these two equations, if I divide this by this, I'll get u into 2 cos theta is this divided by this. So that's how much? 60. So that is telling me that u cos theta is also 60. Sorry, is also 30. Okay, so now I have the very interesting result that u cos theta, or the horizontal component of initial velocity, is equal to 30 meters per second. U sine theta, or the vertical component of initial velocity, is also 30 meters per second. That means the initial velocity is 30 I cap plus 30 j cap, which means that it has a magnitude of 30 root 2, and its angle of projection is 45 degrees. So this I have got first of all. Yes, very good, Manav. That's correct. No, Rishikesh, the maximum height will be different from what you have said. Just check your calculation. It should be half of what you have given as the answer. So anyway, now I'm working out the different parts. So we want to find out the maximum height. So that is given by the formula u square sine square theta by 2g, or that's the same thing as uy square by 2g. So here you can see it will be 900 divided by 20. So the maximum height will come out to be 45 meters. Yes, once that's correct. Arushi, that's correct. Very good. Now next what we have to do, we have to find capital T and T2. So this is where we can use the symmetry thing. Capital T of course is from a formula 2u sine theta by g, or 2 times uy by g. So from that you'll see you'll get the total time of flight as 6 seconds. Okay. Now you can use the symmetry that T2 should be equal to T minus T1, where T1 was 2 seconds. Okay, T2 we want to find out because the y component of displacement is the same, equal to 40 meters at T1 and T2. So use that symmetry. So from that you will see that T2 comes out to be 4 seconds. I'll show you the normal equation solving method also. It's a little bit more lengthy, but you can do it by that also. But this shows you how much easier it is. So this is the shortcut method. Okay, this is where I'm using the shortcut, which is the symmetry of the motion. So if the y coordinate is the same at T1 and T2, then T2 should be capital T minus T1. Okay. Otherwise, what I have to do is I have to use that fundamental equation. If I'm not using symmetry, or alternately, what I'll do is I'll use this equation: y is equal to u sine theta t minus half gt square. So y is equal to 30t minus 5t square. Now in this equation, when we substitute y as 40 meters, the two roots, okay, t1 should be 2 seconds and t2 should be the other one. Okay. So do that substitution and you can see you get, so 40 is equal to 30t minus 5t square, or t square minus 6t plus 8 is equal to 0. So you see that you get these two roots. But as I said, this equation solving was not required because I could have directly used the symmetry, which directly gives me the answer, that is 6 minus 2 or 4 seconds. B part beta is the formula. This is the formula for maximum height. It's a standard formula. So I've not done any, derivation or anything over here. Priya, move this is clear now, beta.
Yes, sir.
Okay. Yeah, very good. Bunch your answers are correct. Okay, so I think we're almost done with the question. Now just we have to find the velocity at the highest point. So that will be the horizontal component of velocity. So that's pretty obvious. At the highest point, what will happen is not only that, the time will be 3 seconds. The velocity will be just the horizontal component. So it will be 30 I cap in meters per second. The y coordinate will be the maximum height, which we saw as 45 meters. And the x coordinate will be half the range. So it will be 90 meters. So those will be the properties of that point. When it's at this position here, so it will be 30 meters per second. The time will be 3 seconds. This height will be 45 meters, and this distance from here to here will be 90 meters. So this is also 90 meters. The next thing we come to in projectile motion is equation of trajectory. Still we are discussing about the standard projectile motion. So the word trajectory is basically a fancy word for the term path. Trajectory is the same thing as path. So having defined the reference frame in the same way that the origin is taken at the point of projection and x and y axis are horizontal and vertical respectively. Now we want to write an equation that represents this actual path of the projectile. So this actual curve that it moves along, it's basically the graph of some function. We want to find out that relationship or that function. So this is the path or trajectory. So we want to find an equation that is a relationship between x and y to define this trajectory. So that is what we do when we find the equation of trajectory. And not only it's a matter of finding the equation of trajectory, we will see that equation of trajectory can be used as yet another tool for solving problems. Okay. So far what we know is that if this is the position of the particle at t equal to 0 and that's the velocity, then at any general time t, we know how to write x and y coordinates as functions of time. So we can use that only to find the relationship between x and y, which will be the equation of trajectory. So we know x is equal to u cos theta t and y is equal to u sin theta t minus half gt square. So what these two equations are doing is they represent position, that is the xy coordinate, as a function of time. Okay. So now from these equations, if we eliminate the variable t by solving them, then it will result in an equation. It will result in a relationship between x and y. So that relationship will become the equation of trajectory. It will represent the path of the particle as it is going in projectile motion. So how to do this operation mathematically now is that from equation 1, you can represent time as x upon u cos theta. At some time t, if the x coordinate is x, then the value of the time is x divided by u cos theta. Now substitute t in terms of x in the second equation, so that we get rid of t. So y is equal to u sine theta into t. Now in place of t, we will substitute x by u cos theta minus half gt square. So again, in place of t, we will substitute x divided by u cos theta. So now see the relationship that we are getting, it does not involve time anymore. It's a pure relationship between x and y. So that represents the equation of trajectory. So just tidying out the terms, we get something like this. So this now represents the equation of trajectory. Every point on the xy plane through which that particle has traveled, each point will satisfy this particular equation. So this equation represents the trajectory or the path. Now we'll discuss further about it, like the shape of the path we'll understand from the equation comes out to be a parabola, because the equation is quadratic in nature, and plus some more interesting aspects we will understand from that. So let's just note down the basics of this part first. So first of all, note down what is the meaning of equation. Yes, and then how we derive it.
Sir,
Yes.
those equation of trajectory should be a function of time. Sir, but time is not there. So how is it a function of time?
It is not a function of time, beta. Wait, so that's what I've written on top over here. The equation of trajectory is a relationship between x and y that represents the
Oh,
path.
अच्छा, अच्छा, blue
Okay.
part.
Understand? We already know the path as a function of time. We know x coordinate as a function of time and y coordinate as a function of time. Those are my equations 1 and 2. But now from those equations, what I'm trying to find out is the relationship between x and y, not involving time, but the pure relationship between x and y. So that represents now the equation of trajectory.
Yes.
Okay, so let's analyze this equation of trajectory a little bit more closely first. So first and foremost, what we can understand is that the equation is a quadratic function or a quadratic equation of y in terms of x. So that basically means that the trajectory or the path of the projectile is a parabola. Okay, the actual path that it follows, this shape that we discussed earlier, that shape is a parabola. That's the first point. The second point is that the equation can also be written as, so the equation can also be written in terms of range r and theta. Let's see how that is done. So in this equation, what we do is we'll take x tan theta common first of all. So this will become 1 minus gx square upon u square, rather 2u square cos square theta into tan theta, because I've also taken one tan theta outside. So I have to put a tan theta in the denominator. Now notice that 2u square cos square theta into tan theta is basically equal to 2u square sin theta cos theta, which is basically equal to u square sin 2 theta. Okay. And we know that range is equal to u square sin 2 theta divided by g. So this equation therefore now becomes that y is equal to x tan theta into 1 minus x by r. So this is the same equation but written in a different form, where we are first of all writing it in factorized kind of form instead of directly as a quadratic equation. Factorized way we are writing it, x tan theta into this factor, and we are writing it in terms of r and theta, that is the range and the angle of projection, instead of in terms of u and theta. So this is another way of writing the same equation. This is the equation of trajectory in terms of capital R and theta. Okay, so this comes in very handy in certain types of situations we'll discuss. Just make a note of this quickly first.
Sir,
Yes.
sir, shouldn't it be x tan theta into 1 minus x squared by r?
It should be x only, better, because see, we have taken x common outside. Here, the x square should be removed.
Yes, sir.
Right, no? Yeah. This one make a correction. Here, it should not be x square. It should be just x. So you've taken x tan theta common, no? So inside will be just left with x and an additional tan theta in the denominator. Okay, so now mainly we look at certain types of questions where this method, this equation of trajectory is very useful. Okay, so application examples. Of equation of trajectory. So basically what we should keep in mind is that anything where we have to solve something related to geometry and position, okay, any numerical problem involving position, that is x, y, and the geometry of the path, okay, can easily be solved by equation of trajectory. Okay, whereas any problem involving time, okay, should be solved by time-based equations. That is, x is equal to u cos theta t, y is equal to u sin theta t minus half gt square. These type of equations. Okay. So just keep this guideline in mind. Okay. There's no hard and fast rule that you have to use one method for one type and the other method, but I'm saying it becomes easier. So for example, suppose we have a question like this: a projectile has a range of 480 meters and a maximum height of 90 meters. So find the angle of projection. Yeah. And find its height from the ground at an instant when the horizontal displacement is (180 meters). Okay, take the value of g as 10 meters per second square. Now just try to solve this question by the guideline that I showed you on top. Notice that in the question we're only talking about the geometry of the problem, that what is the range, what is the maximum height, what is the angle of projection we have to calculate. We're not solving anything to do with time, that at how much time it's reaching this position, or the time of flight is so much, etc. So in such a situation, you should avoid equation using the time-based equations, because you will have to find the time and then eliminate it. Whereas if you use the equation of trajectory, then there's no involvement of time in that equation. So it will be more efficient. It will be easier to solve it by using that method. So this is just to help you understand that point. What type of questions we generally attempt using the equation of trajectory. Yes, very good. 37 degrees is the right answer. So the thing is, you can do this by formula-based method, or you can also do it by equation of trajectory method, which is very easy. If you look at the equation of trajectory, it is y is equal to x tan theta into 1 minus x by r, where over here the range is equal to 480 meters. Also, the maximum height is given to us as 90 meters. Now we know from the symmetry of the projectile motion that when it reaches the highest point, the x coordinate is how much? R by 2. So we know that this point over here, it has the coordinates r by 2 comma h. So this equation is satisfied by the highest point. At the highest point, the x coordinate should be r by 2. So that should be 240 meters. And the y coordinate should be h, which should be 90 meters. So substitute that in the equation of trajectory. So we have 90 is equal to 240 tan theta into 1 minus 240 divided by 480. So that will give us that 90 is equal to 120 tan theta. So tan theta is 3 by 4. That means theta is 37 degrees. This gives a very efficient way of solving something like this. And now the second part also, once we know this, so we know the equation of trajectory is now becoming y is equal to 3 by 4x into 1 minus x upon 480. This is the equation of trajectory. Okay. So now the second part of the question, we have to find y when x is equal to 180 meters. We can do that from here. Okay. Y will become 3 by 4 into 180 into 1 minus 180 divided by 480. That is 3 into 45 into 1 minus 3 by 8. Okay, so that is going to be how much now? So this is the height above the ground when x is equal to 180 meters. So you can see the solving is quite easy by using equation of trajectory. Whereas if you had tried to use the fundamental equations which are time based, you would end up solving a whole lot of things. You would end up finding the time at which x is 180, then solve for that y. And before that, you would have to calculate the value of u to be able to get those time based equations and all. So this is something to keep in mind while solving projectile motion questions. The questions which are based on the geometry of the path or based on the coordinates x, y, and things like that, we can usually solve more easily by using equation of trajectory. Okay, so this is clear to all of you. Okay, so hope this question was clear. Now the last situation we will see in projectile motion before we wind this up and come to the doubts is we will see projectile motion with the projection from an elevated point. Elevated or heighted point. This is not something difficult in any way. It's just that we have to adjust the equation slightly. So for example, the first case we'll take is that from a certain height above the ground, if we project or throw an object horizontally, then how we can find out the time taken to reach the ground and all these things. So we'll solve this as an example only. So the first example, we'll take horizontal projection from a height. So let's say this height is 320 meters. And from here, at time t equal to 0, what we're doing is we are projecting something horizontally at a speed of 80 meters per second. So you take the value of g as 10 meters per second square. So this particle will set off like this and gravity will pull it down and it will come and eventually hit the ground. So what we want to do is, first of all, we want to find the velocity and displacement at time t. Okay. And suppose it hits the ground at time capital T. And this horizontal distance from here to here is r. We also want to find capital T, that is time when it hits the ground. And we also want to find the impact velocity with the ground. We also want to find the range, or the horizontal distance at which it lands on the ground. Okay. So just make a note of this situation, then we'll see how to solve it. So the same approach that we have taken to projectile motion earlier, only difference is now the initial velocity has only got x component, it has not got a y component. There the components of velocity were u cos theta horizontal and u sin theta vertical. Here the components of velocity are u and 0 for vertical. The rest, the method of solving is more or less the same. Okay. So while we can't use the direct formula for r and all that because this is a different situation, but we can use a very similar method to generate the equations of motion. That is how x is varying with time, how y is varying with time, how velocity is varying with time. And from that we can easily solve these things.
So we could have also projected
We could have also-
it in such a way that it goes upwards for some time and then comes down.
Yes, we can obliquely project also, and also we can also project in such a way that it directly goes down. All the three situations are possible. We can project it like this, we can also project it like this, or we can project it horizontally, like we've done over here. All such different possibilities are there, and each case we have to slightly adjust how we solve the problem. So let's understand that first. Okay, so what we'll do is, here since it's straight away got 0 vertical velocity, and because of gravity it's going to go in the downward direction, we will take our y-axis downwards. It will be more convenient to do that. So if we take our reference frame in the same way, okay, so at some time t when it reaches here, we want to find x and y coordinates and the velocity. Yeah, I'll scroll up. Okay. So we'll take a reference frame in this way, that x-axis is horizontal, y-axis is vertically downwards. not upwards. And the origin is at the point of projection. So now what you do is write the equations in component form. I'll take you back to the question. Just give me a moment. Along the y-axis, you write what is ux, what is ax, what is uy, what is ay. And then from that you generate the equations that what is x as a function of time, what is y as a function of time, what is vx as a function of time, what is vy as a function of time, and solve for the various things. Okay. So this is the general approach. Just try it out. Okay. Of course, there is no hard and fast rule. You can still take the y-axis upwards. Okay. I'm just telling you what will work out more convenient when you're trying to solve the question numerically. Okay. What will work out more convenient here is if we take the y-axis downwards. So please try to work this question out, people. Okay, very good. So let's solve this. Yeah, Manav, your analysis is correct. Okay. So according to the reference frame that I have taken here, which is that y-axis is downwards. Okay. The sign convention should be anything downwards is positive. So my initial velocity is x component is u, which is 80 meters per second, but acceleration is 0, whereas initial velocity is y component is 0, whereas the acceleration is g, or 10 meters per second square. So now from that I can see that I'll get at time t, Vx is 80, whereas x coordinate will be 80 t in meters, and Vy will be half gt square. Sorry, Vy will be gt. Y coordinate will be half gt square, or in this case 5t square in meters. So x is 80t, y is 5t square, and the velocity is 80 I cap plus 10t j cap. The j cap of course means downwards here. The y displacement is also downwards. Very good, Anand, that's correct. T is equal to 8 seconds is the total time. So this solves the first part. Okay. The position and velocity as a function of time. Now second thing, at t equal to capital T, you can see the y coordinate is h, because it's made a downward displacement of h. So you can see that h should be equal to half gt square, or 320 should be equal to 5t square. From this we'll get t as 8 seconds. And then we can see that the impact velocity will be velocity at capital T. So that is 80 I cap plus 10 into 8 j cap. So the impact velocity will be interestingly 80 I cap plus 80 j cap, or it will have a magnitude of 80 root 2, and we at 45 degrees like this. This angle further you can see will be 45 degrees, because the x and y component are equal in magnitude. So hope this is also clear. Now just one thing remaining, the r, the value of capital R we have to find out. So just see if you can figure that out yourself. Okay. Now after this we'll come to the doubts. So if there are any questions from the worksheet which I had sent for motion along a straight line before we started projectile motion, before your MT3 in fact. Very good, that's correct, Anand. So please start sending me the questions that you have now sent, especially from that worksheet, or if there's anything from HC you can send that also. You can send me the question number on the text message, or you can WhatsApp me, whichever be the case. Okay, so I'm first solving for the range and then I will come to the questions that have been said. So over here you can see that at t equal to capital T, which we have calculated to be 8 seconds, the x coordinate is equal to r, okay, at this point over here. So x is equal to 80t, that means this range should be equal to 80 capital T. So it should become 640 meters. So it will land at a distance which is horizontally 640 meters from the point vertically below where we had projected it. So good, Anand, your answer was correct. Okay, Shayan, I've received your message. So I'm coming to question 24 of the objective type. This you are saying from the worksheet which I have sent, right? From practice sheet 1, right, Shayan?
Yes, sir.
Okay. Okay, so objective type, we will start with question number 6, 10, and 13, coming on to 24 eventually. So I'm starting with question number 6 of the objective type, 6 and 10. Adinath, you have asked these two questions first of all. So let's look at the sixth one. It says point moves with uniform acceleration and V1, V2, and V3 denote the average velocities in 3 successive intervals of time T1, T2, and T3. Which of the relations is correct? Okay. So V1 is equal to average velocity from, let's say, T equal to 0 to T equal to T1. V2 is the average velocity from T equal to T1 to T equal to T1 plus T2, because the interval of time should be delta T should be equal to T2. Okay. And similarly, V3 is the average velocity from T equal to T2 plus T1 to T1 plus T2 plus T3. This is the interval of time being this. Okay. Now we have to find the relation between this. Now see, when acceleration is uniform,
Sir,
yes,
sir, for V3, how did you get from T equal to T1 plus T2?
because it's saying 3 successive intervals of time. You understanding? No? So for example, if you plot velocity versus time, okay. Now from this graph, you'll understand how I got that. Now suppose this is the, graph, because it's a straight line. Okay. Now suppose this time is T1. Okay. Now so this interval from 0 to T1, this is an interval of time equal to T1 seconds, right? Now
Yes.
from here, I want the second interval of time, which is of how much? T2. तो
Yes.
second interval of time के बाद में जो time होगा at the end of that interval, what will be the value of time? It will be
Yeah.
t1 plus t2. ना? Okay. And
Yes.
from here I want a third interval, which is how much? T3. So that third interval should take you from this point to this point, such that the time has increased by t3. Na? So this will be t1 plus t2 plus t3.
Yes, sir. Got it.
Okay. No. Okay. Okay. So now we want to find the relation between these things. Okay. Now in this graph, what is the meaning of average velocity actually? So suppose the velocity exactly at initial velocity was suppose u. Okay. Then the velocity at t1 was suppose I'm writing it now as va because we already use v1 and all this. Okay. And the velocity at this time was vb, and the velocity at this time was vc. Now you know that, remember we had discussed that in uniform acceleration, in uniformly accelerated motion, average velocity in a time interval is what? It is initial velocity plus final velocity divided by 2. You remember this fact, people? Okay.
Yes.
So we have u plus va by 2 is equal to v1 because of this factory. Okay. And also we have that va minus u upon t1 is equal to e. V minus u upon t is equal to the acceleration. Okay. So v is the instantaneous velocity. It's not the average velocity. This is the instantaneous velocity at t equal to t1. Like that, vb is at this time. Okay. So now from this statement, we will see that the average of va and vb is equal to v2, and further we have vb minus va divided by t2 is equal to e. Okay. So that we have here. And then finally from this statement here, we have another similar statement that vb plus vc by 2 is equal to v3. Okay. And yeah, people just got disconnected for a moment. Okay. So now, for example, in Okay, so I've just illustrated this. I'll explain this point again, how it's working out. So hope these three equations were clear. Okay. Using the fact that average velocity in an interval of time is the initial velocity plus the final velocity is arithmetic mean. So this is the statement about VA. This is the statement about VB. And this is the statement about V3. And also using the relation that V is equal to U plus AT. That means V minus U by T is equal to A. Okay. So we have these three relations. So now what we have to find in the question is the ratio of V1 minus V2 is to V2 minus V3. So write V1 minus V2 in terms of equation 1 and 2. Okay. So this is coming from equation 1 and 2 above. And similarly write V2 minus V3 as this by subtracting these two equations. So it's coming from equation 2 and 3. Okay. And then further from this equation, you can see you can substitute VA as U plus AT1, VB as U plus A into T1 plus T2. And like that, VC as this. So we can easily substitute these terms here and we get this answer. Okay.
Yes, sir.
So hope this question is clear.
Yes.
Moving on to the 10th one. Okay. The same exercise, the objective exercise. Okay, so it says motors of an electric train can give it an acceleration of 1 and the brakes can give it a deceleration or negative acceleration of 3. The shortest time in which the train can make the trip between two stations, which are 1215 meters apart, is how much? Okay. So the thing is, if the train is making the trip in the shortest time, then it should accelerate for the longest period of time. It should not travel at too much time at uniform velocity. So basically for the shortest time, what we want is that the velocity time graph should be such that for the longest possible amount of time, the train directly accelerates. And after that, it directly decelerates. Then the time factor will be the shortest. Now, when it is accelerating, this acceleration is plus 1 meters per second square. And when it's at the deceleration phase, the deceleration is 3 meters per second square. So suppose it accelerates for some time t1 and then decelerates for some time t2. So the total time is like this. Now, what should be the area under this graph? This area should be equal to the displacement, which should be the distance between the two trains. So you realize that if it does this, in this case, the time will be minimum total time. Whereas as opposed to this, it also has the option of doing something like this, where instead of accelerating for the longest possible time, it accelerates for a limited amount of time and chooses to go at constant velocity and then decelerates. So the moment you compare the two graphs, you will see that this will involve more time because you want to cover the same area, but then you have a flat top. So you will require a longer base. Now this area will also have to be the total displacement, which is 1215. But in this case, it is accelerating for some time. We have to a time t1. Then it is going with uniform velocity for some more time. So t1 plus t2. And then finally it's decelerating here and coming to rest at t1 plus t2 plus t3. So in this case, you will see that definitely what will happen, that the total time taken will be more, because if you compare the two graphs, you want this area to be equal to this area. So if both the areas are the same, then obviously the triangle has a shorter base. Okay, so it has less amount of time taken. So this is the minimum time case, whereas in this case, the total time taken will be more. Okay, so hope this question is also clear.
Yes, sir.
Okay. Fortunately, I've lost the group of messages because I was logged out. So from memory, I think question 20 was there in it and question 24. If there's anything before question 20, please drop me a message. Between 10 and 20, if there's any other question you have a doubt in. Okay, question 13, 17. Okay, so let's try to go serially then. Okay, so let's understand this visually. So let us say that this is the straight track on which the two trains are going, and this is the engine of the first train, and this is the engine of the second train coming from the opposite direction. Okay, so the driver of this one is moving at V, finds a good train is moving with a velocity, so probably this V1, and this is moving at a velocity V2. Oh, it is moving in the same direction on the same track. So it's moving in the same direction like this. Okay. Okay, so what will happen is, now suppose this is moving with zero acceleration, so it is at uniform speed. Okay. But V1 is greater than V2. So what will happen if this was the situation at t equal to 0? Then after some time, the gap between them will reduce. If this gap was d, okay, the gap will start reducing because V1 is greater than V2. So what we want to avoid collision, we want to apply a deceleration like this. So on applying a deceleration, the speed of the first train at time t will become the initial velocity V1 minus at. Okay, and VB will of course remain constant at V2, because that one is not accelerating or braking, either of the two. So we'll assume this. Okay, so and if collision is to be avoided altogether, then the speed of the train A should become less than or at best equal to the speed of the train B. So V1 minus at should become less than equal to V2. So you can see time should become greater than equal to V1 minus V2 by E. So the minimum amount of time required is this one, V1 minus V2 divided by E, because in so much time what happens that the train speed becomes the same as the second train speed. So after that, there is no chance of collision. But up till the speeds are becoming equal, V1 is greater, VA is greater than VB. So what will happen is, so after some time here at time t, this one's speed has become V1 minus at. But at that point of time, this one's speed is maintained at V2. Okay. So as long as VA is greater than VB, there is a chance of collision because A is moving faster than B. But the moment A's speed becomes equal to or after that becomes less, then there's no more chance of collision. So that minimum time taken to avoid collision is this much. Is this question also clear? Adinath, this is clear, beta?
Yes, sir.
Okay. Let's move on to 17th question. We'll take another 5 minutes or so and try to see maximum number of questions solved by them. Don't worry, we'll keep more time for doubts also. Plus, you'll have mentorship sessions also. We'll discuss during those also. Okay, now 17th question. You have 3 different balls which are allowed to roll from west on 3 frictionless paths. Okay, OB is almost a vertical path. height of O above the ground is h. Okay. So basically, the idea is if I compare two paths like this, forget about this question exactly for a moment. Okay, let's take a slightly different diagram where suppose I have two different paths. One is this path. So one object A starts sliding from here at t equal to 0. When the other object B also starts sliding. So after some time, A is here and B would be somewhere over here. So suppose you want to compare the time taken by A and B, then we'll come back to this question. Okay. So we want to compare the time taken by A and B. So you can see that by the time A reaches the ground here, let's say the time is TA, and by the time B reaches the ground here, the time is TB. So from 0 to TA, what is the displacement of A? It is this hypotenuse. So if this angle is theta, it is h by sine theta. Okay, and from 0 to TB, what is the displacement of B? It is h by sine. Let's say this angle is phi, so it is h by sine phi. Okay. Now from your Newton's laws of motion, you know that this is a smooth surface. So what is the acceleration of A? And similarly, what is the acceleration of B? So from NLM concept, you know that the acceleration of A is g sine theta, and the acceleration of B is also g sine phi. So the displacement of A should be equal to half AT square. The displacement of B should be equal to AT square. Okay. And also, if this reaches, we want to find the final velocities, not the time. So this reaches with the velocity VA and this reaches with the velocity VB. So we also know that VA square is equal to 2 times, okay, and VB square is equal to 2 times acceleration of B into displacement of B. So if you want to compare the time, which is not the case in this particular question, then you have to use the half AT square equations. So from these two equations, you can see that SA by SB will be equal to acceleration of A divided by acceleration of B into TA by TB whole square. So from this, if required, we could find the ratio of TAs to TB. But now in this particular question, we are more interested in this actually. So VA by VB, their final speed square is the ratio of their accelerations into the ratio of their displacements. Now you can see this ratio would be 1 because the accelerations are like this. This acceleration of A divided by acceleration of B is sine theta by sine phi. Okay, and displacement of A divided by displacement of B is sine phi divided by sine theta. So therefore, you can see that this ratio is 1. So therefore, VA is equal to VB. Okay. Now, what we have discussed about this will also work for a situation where instead of a straight path, it is like this. Okay. Even if this happens, as long as they are both coming down through the same height, they'll come at different times, but their speeds will be the same at the lowest point. VA will be equal to VB. TA will not be equal to TB. The time will be different, which you can see from here. This ratio will not be 1:1, but this ratio will be 1:1. Okay, so hope this question is also clear.
Yes, sir.
Let's move on to the 20th question. In 20th question, a ball is thrown up vertically from the ground at t equal to 0. You want to represent the velocity time graph ignoring air resistance. So at any time t, you know that the velocity is actually given by the relation u minus gt. So the proper velocity time graph will be like the one we had drawn earlier. But I think in this question, you have to give the speed versus time graph instead of the velocity versus time graph. So we'll discuss that also. So the velocity time graph will be like this. It starts from the ground with plus u. Then at half time, the velocity becomes 0. And after half time, the velocity starts becoming negative, such that at total time of flight, the velocity should become minus u. So this is actually the velocity time graph. When we write it, when we make it properly with the algebraic sign and all that. But if we just take magnitude of velocity or speed versus time graph, then we'll have to modify this a little bit. Okay, so mod v or speed versus time graph. Probably in the question, what is meant by the question, according to the graphs they're given as options, is actually this. Because it's not showing the velocity becoming negative anywhere, so we'll have to assume that they've taken only mod of velocity. In other words, they've taken speed. So that will become like this. Okay,
Yes.
so actually, you can correct the language of the question a little bit. You can make it the speed versus time graph or magnitude of velocity versus time. So that one is this. Okay. So hope this is also clear. Okay, people, we will have to conclude today's session, but next session, again, I will keep time for discussing the doubts, and especially by then you would have done questions of projectile motion. I'll send you a list of questions from HCV plus an exercise. So we'll look at the doubts of 1D motion as well as projectile motion together. Okay, so that's it for today's session, people. Thanks for attending. Wish you all the best. Have a nice day.
Thank you.
Thank you so much.
Thank you, sir.